All right, what we are going to talk about today is an introduction to amplifier circuits. So an amplifier is an electrical circuit or device which increases the magnitude of the signal applied at its input. Let's say that we have a input and output perspective of an amplifier, where on the left-hand side of my page will be the input side of the amplifier. So these are its input terminals. And then I'm going to represent, for now, my amplifier as a simple black box network. And over here, on the right-hand side are my output terminals. If our input signal is x of t, and this input signal could be a voltage, a current, or a power, and our output signal y of t could be a current, voltage, or power, then we can define the gain of the amplifier A to be the ratio of the output signal divided by the input signal. Another way a system like this can be represented is with a signal flow diagram representation, which would look something like this, where we have, again, our input signal on the left-hand side, x of t, our amplifier here in the middle that has some gain A, and then over here on the right-hand side, we have our output y of t, which would be given by A multiplied by or acting on our input signal of t. So these are the two basic ways that you might see generic amplifiers implemented. There are multiple different types of amplifiers, and we are going to classify some of them today. I'm going to restrict our analysis to input-output classifications because talking about transistor amplifiers and things like that are beyond the scope of this course. So I'm going to make a simple table here where we're going to look at our input signal, our output signal, and then give our amplifier a name. So for our first amplifier type, let's consider when we have a voltage signal at the input, and we measure a voltage signal at the output, we have, unsurprisingly, a voltage amplifier. If we have a current at the input, current at the output, then we have a current amplifier. If we apply a voltage at the input and measure a current at the output, we have a transconductance amplifier. If we have a current at the input, voltage at the output, we have a trans resistance, or more commonly, trans impedance amplifier. And lastly, if our input signal is a power waveform, and our output signal is a power waveform, we have a power amplifier. Now, you may not be aware of this, but we actually deal with several of these different types of amplifiers on a daily basis. For example, when I drove to work this morning from my home in Minden, in my car, I listened to the radio. To be able to listen to a radio broadcast requires the use of a voltage amplifier, actually a preamp, which converts the electromagnetic signal that hits my antenna and demodulates that down into a smaller signal. And then that signal gets passed through a power amplifier, which effectively gives the signal enough energy to drive my speakers. In our cell phones, we have multiple different transconductance, transimpedance, current, and voltage amplifiers all over it to do various forms of the signal processing that is required to take a signal from a cell tower and convert it into something that we as an end user can interact with. So almost all of these amplifier types are in wide usage, literally all around us, and we likely don't even know. So we are going to constrain our analysis today by really getting into the nitty-gritty of a voltage amplifier circuit. So a classic voltage amplifier circuit might look something like this. Here we have our black box representation of our voltage amplifier. This is the signal Vn of t. This is the signal V out of t. The amplifier acts on that input signal to create that output signal. So I'm just going to label this down here. Amplifier. On the left-hand side, we're going to have some sort of source, and I'm going to realize this as a practical voltage source. So it will have some series resistance RS that's characteristic of the source. And our signal that's being amplified will be Vs of t. So this is our source side of our system. And then on the right-hand side, I'm going to represent our load as just a simple resistive load. It's likely not always the case, or it's actually definitely not always the case. But we could be driving capacitive loads, light bank speakers, anything that we really want to provide a signal to. And I'm going to call this VL of T, where, just to be clear, the L in this case stands for load. I'm not trying to introduce an inductance into our system. So this is a very simplified view of a voltage amplifier circuit, okay? We can break it down into the source stage, which is providing a signal to the amplifier stage, which amplifies that source signal, and then the load stage, which takes the amplified signal and does something with it, okay? This type of drawing is actually representative of any voltage amplifier circuit, okay? And we're going to analyze this circuit with the inclusion of this black box network amplifier, as opposed to analyzing a more detailed amplifier circuit because of the complexity associated with an actual amplifier circuit. To show you what I mean, I'd like to open up a file here. I need to find real quick. There we go. And I believe it's on page 9. Oh, page 10. All right, and I'm going to zoom out just a smidge. Okay, this terrifying looking circuit is a actually quite simple operational amplifier, which is a voltage amplifier that has a differential voltage input and outputs a single-ended voltage signal. This particular circuit, if I scroll down here, contains 22 transistors, 11 resistors, 1 diode, and 1 capacitor. Analyzing a circuit of this complexity, even though this is a simple operational amplifier, is well beyond the scope of this class. Instead, what we're going to do is represent this amplifier circuit by 3 key parameters. So, using just simply Thevenin equivalent circuits, if we were to look in, let me do this in blue. Look into the input terminals of our amplifier, what we would see would be called the input resistance of our amplifier. If we looked in to the output terminals of our amplifier, just using again Thevenin equivalent circuits, we would see the output resistance, and then we know that the amplifier itself is characterized by its gain, A. I'm going to call this AVOL, where the V stands for voltage and OL is open loop. So this is the open loop voltage gain, simply defined as the ratio V out over V in of t. It's these three parameters, R in, R out, and AVOL, that define the behavior of any voltage amplifier. So I'm now going to modify our simple representation of a voltage amplifier to include these quantities directly. So now, instead of seeing a black box representation, when we look into our amplifier circuit, we are going to see a resistance, Rn. This dependent source here is taking care of the amplification. So we're going to have A VOL times Vn. And then here we have our resistance out. This is our voltage for our amplifier, Vn of t. This is our output voltage, V out of t. And then we would connect our load and our signal source, like so. And I'm going to put a box around this bit here in the middle and give it a name. This is what we are going to refer to as our practical amplifier model. Used again to analyze any amplifier circuit, particularly voltage amplifier circuits, where we're not particularly concerned with the exact behavior of the internal workings of the amplifier. We're more so concerned with how it behaves as a signal processing unit. Okay. Now, in this class, we are going to be talking about operational amplifiers a lot. Our first module that'll span a few weeks is all about op amps. As I mentioned previously, and we can see it here if we pop back over to this screen, our op amp circuit has two input voltages. In minus, which is for our inverting input, and in plus, which is for our non-inverting input. The model that we've developed here only has a single input. So we're going to have to make a very slight modification to take into account that an op amp is what's called a differential amplifier. So our practical op amp model will look like this. So I'm going to have my input resistance Rn, like so. And I'm going to call this voltage up top V plus, which is where our non-inverting input terminal is. G, not a P. I'm going to have this terminal labeled with V minus. This is for our inverting input. And I'm going to call the potential difference between these two voltages VD, our differential voltage. So that takes care of the input side. Now we'll work on the output side of the op amp model. So I have my dependent voltage source. In this case, it's going to have a gain of AVOL, so it still has an open loop gain. But instead of acting on V plus or V minus, because it's a differential amplifier, it acts on our differential voltage VD. So an op amp's ostensible primary function is to amplify a potential difference seen at its input terminals to generate some output voltage. I'm going to have my output resistance up here. Like so. And what I'm going to do now is I'm going to give everything here a reference simply by having a bottom node that is grounded. Here is my output terminal. And I could also just as easily say then that this voltage is my output voltage. And I'm kind of running out of room a little bit here. This voltage is my inverting input voltage. And this voltage is my non-inverting input voltage. This is the model that we are going to use to represent the schematic representation of an op amp that we're familiar with, which is this triangular guy right here, where the voltage associated with the plus sign is the non-inverting input voltage. The voltage associated with the minus sign is the inverting input voltage. And on the right-hand side here, we have our output voltage. So what I would like for us to do now is to work a simple example problem to introduce some of the limitations of this model. Okay. So if we were asked to determine the behavior of the following circuit. Using the practical op-amp model, how would we go about doing this? Well, first thing I need to do is I need to know what my op-amp parameters are, right? So let's say that our open loop voltage gain, AVOL, is equal to 100,000 volts per volts. For an operational amplifier, this is fairly typical. The Texas Instruments 741 amplifier that I have been referencing here actually has an open loop gain of about 200,000 volts per volt. Okay. Some special purpose amplifiers or op-amps may have voltage gains that are a little bit lower. Some may have voltage gains that are as much as a few million, but typically speaking, we should expect to see a voltage gain of at least several thousand volts per volt from an op-amp. My input resistance, Rn, will be 1 mega ohm. Again, this is a very typical value for operational amplifiers that are based on bipolar junction transistor technology. Input resistances on the order of single to tens of mega ohms is very common. For operational amplifiers that are based on MOSFET transistors, input resistances of single digit tera ohms or 10 to the 12 ohms is very common. So 1 mega ohm is a very, very reasonable value for an input resistance. And finally, our output resistance is going to be 25 ohms. An output resistance of 25 ohms, again, is fairly typical. You may see output resistances as high as 100 ohms in a well-designed op-amp and as low as in the milliohm range for very well-designed op-amps. We'll see why these values play a critical role in a bit, okay? So we have a circuit, we have our op-amp parameters. So what I'm going to do now is I'm going to redraw this circuit using our practical op-amp model. So how I choose to do this is I start with the op-amp first and then make all of the other connections as are necessary. So here's my non-inverting input. Here's my input resistance of 1 mega ohm. Here's my inverting input signal terminal. Here is my dependent source. 100,000 is the same as 10 to the 5, so I'm just going to call this 10 to the 5 VD. And over here on the left, I'm going to make sure to write VD. VD, our differential voltage, will always be the difference between our non-inverting input terminal and our inverting input terminal. And then I have output resistance, which is 25 ohms. I'm going to draw my ground node down here. All right, so this is my op amp portion. So now we need to look at everything else, okay? So my inverting input terminal is connected directly to ground. So I'm just going to put a short circuit right here, which connects that node directly to ground. My non-inverting input terminal has a 1 volt source connected between that terminal and ground. So I'm going to represent that with a 1 volt source over here on the left-hand side. My output node is open circuited, so I'm going to just have my output voltage V out here, the voltage drop over this open circuit at the output side of my amplifier. So this is what my practical representation of the op amp circuit described above would look like. One thing that I want to point out, and we'll get into this in a moment, is these voltages right here. VCC plus, which I have set equal to 10 volts, and VCC minus, which I have set equal to negative 10 volts. Operational amplifiers are an example of an active device, where an active device is one that simply needs some form of external power in order to perform its function correctly. Our model does not have any means by which to reference these power supply voltages, okay? So keep that in the back of your mind for a moment. Now let's do some analysis here, okay? Purely by inspection, I can say that my output voltage, V out, is going to be 10 to the 5 times my differential voltage, VD. I say that because my 25 ohm resistor isn't part of a closed current carrying loop, which means the voltage drop over the 25 ohm resistor must be 0, and therefore V out is simply the voltage being provided by my dependent voltage source, okay? So I'd like to ask you guys what our differential voltage VD is in this case. So somebody got terrified and dropped out of Zoom when I asked this question. Anybody have any thoughts? Yeah, it's just 1 volt, right? So the voltage measured at the non-inverting input terminal with respect to ground is 1 volt. The voltage measured at the inverting input terminal with respect to ground is 0 volts. And the difference between those two things is simply 1 volt. So from this, V out is 10 to the 5 volts. I'm going to put a question mark here. Does it make sense that our output voltage is 100,000 volts? So we put in 1 volt, we get out 100,000 volts. Everything that I've drawn here says the answer to that question should be yes. What we are neglecting, though, is that this is an active device, right? And so what that means is that our output signal is going to be constrained to fall between our power supply voltages. What this is commonly referred to as saturation distortion. So Saturation distortion simply means that in a real practical op amp, the output voltage, sorry, singular, cannot exceed the power supply voltages VCC plus and VCC minus. Or mathematically, we can define the output voltage for this particular configuration to be something like this. So our output voltage will be VCC plus when AVOL times V plus minus V minus is greater than or equal to VCC plus, which we will call positive saturation. Our output will look like AVOL times V plus minus V minus, or VCC minus is less than AVOL times V plus minus V minus is less than VCC plus, which we will refer to as the linear region of operation. And finally, our output voltage will be VCC minus when AVOL times V plus minus V minus is less than or equal to VCC minus, which we'll call negative saturation. So all of this piecewise definition really means is that our output voltage can never be more positive than our positive power supply voltage, and it can never be more negative than our negative power supply voltage. Now, in truth, this statement is only true for what's called a rail-to-rail op amp. And in a rail-to-rail op amp, it is designed in such a way as to let the output voltage go all the way to the positive and negative supply. Some op amps are not rail-to-rail op amps, and so their maximum output voltage is constrained to be within a volt or so of the power supply voltages. For the sake of this class, we are going to consider every op amp that we analyze to be a rail-to-rail op amp. Okay. So now that we have an understanding of what saturation distortion is, what is the actual output voltage of our amplifier that we were looking at? Well, since 10 to the 5 volts is much, much greater than VCC plus, our actual output voltage is simply VCC plus or 10 volts. So we are at a point where our amplifier is well into the positive saturation region. So to me, this begs the question of what size of input signal could I actually use in this circuit to see linear amplification? And to get that, we're going to have to talk about very briefly what's called the linear range. Okay, so we can finish this down here on this page. So the linear range is simply values of our input signal which yield linear amplification, meaning that our amplifier is actually acting like an amplifier in as much as it is providing a scaled version of the input signal. Okay, and how we determine the linear range is actually very easy. Okay, our linear range is defined by VCC minus divided by the open loop gain, AVOL, is less than VD is less than VCC plus divided by AVOL, which for our circuit works out to be a range of negative 100 microvolts is less than VD is less than positive 100 microvolts, meaning that for any differential signal that is greater in magnitude than 100 microvolts, we will push this amplifier into a saturation region of operation. So this is all that I wanted to talk about for today. On our next class meeting on Wednesday, we are going to talk about circuits that utilize this very small linear range by going over what are called open loop op-amp circuits. When we finish open loop op-amp circuits, we will then move along to looking at closed loop op-amp circuits. We will start with closed loop circuits that employ positive feedback, and we'll talk a bit about positive feedback, what it does to the amplifier, and then how it can be utilized to provide some sort of useful output. Then we will talk about negative feedback operational amplifier circuits, which is what most of you are all currently familiar with from your first circuits classes. So I just wanted to give you a heads up of where we're heading over the next couple of class meetings. Thank you for your time, and I will see you on Wednesday if there are no questions.